Okay, so what is a linear system? And before we understand what a linear system is, I think it's important to understand what a system is. I would claim that we live in a world where we have many systems around us. Every time you drive your car, you're in a system. Every time you fly in an airplane, you're in a system. The stock market in a system. Digital platforms are systems. And they're systems because of the nature of how they work. They take an input, it's like a command, they process that input, and they produce an output. The output is an observation that you have, okay? And so in general, for us to understand these types of input-output behavior, we often have to understand the actual system that is processing them. So we give that a notation, say H, over here. And in our particular context, when we understand inputs and outputs, in the context of time series, these are things that are time-stamped. So in general, for us, the input is really a sequence of time, a sequence in time. So it's something like whatever it is, u of -1, u of 0, u of 1, and then it continues over time. So it starts from -infinity, goes to +infinity. The system processes that and then produces another signal that also starts from -infinity, y of -1, and so forth, okay? That's what we mean when we mean by a system. The H is going to operate from the sequence of inputs to produce a sequence of outputs. Now, the particular representation of a linear time invariant system, I'm going to do it backward. I'm going to tell you what the representation is and come back and tell you why this is a linear and a time invariant system, and what do these actual concepts really mean. The particular operation that this system has is what we call a convolution. And you must have seen that before in previous life. But basically, a convolution is essentially represented in this equation over here. Okay, so what is the convolution equation? It says that to compute or to process and produce the value at time t of the output, the system, which is represented by this kernel over here, acts on all the past values of the input in a particular way. That's what the convolution says, is that there's some convolution kernel. The convolution kernel is associated with the system, and that acts on the input in a particular way to produce the one value of y at time t. And every time t, we have to do this over and over and over. Okay, so it's represented by this equation over here. This is called the convolution equation. I will show you an example in a second of how it actually works in terms of computation. It's fairly straightforward. Okay, notice that in this equation, the summation is over k, a dummy variable that for a given value of t, which is the desired time that we're looking for the output, for a given value, we run this summation for all values of k. So it's kind of a little peculiar. This is h of k, which is the kernel, but then it kind of multiplies u of a shifted version of the input t minus k. I'll show you that graphically in a second. And we often give this a very abstract notation as y as an output is some h acting on u. This is a language I would say it's acting. Okay, it's not that this is multiplying. H is acting, and the way it acts is exactly through the convolution kernel over here. This representation is called a linear system. It's actually a linear time invariant system that I will show you in a second why that is the case. Okay, let's take an example of what we call a discrete integration. So what is a discrete integrator? I'm going to give you the expression, and we will argue whether that actually is a good thing or not. So let's say that the kernel h of t, okay, is equal to this. It's equal to 1 for t greater than or equal to 0, and it's 0 otherwise. Then if you look at what the convolution kernel does, what the convolution operation does, remember, y of t is a summation from k equals minus infinity to infinity, h of k, u of t minus k. Okay? You can change indices over here if you like. Okay? You can change indices and shift it around to write it, and this is the same over k, the same k. But now I'm going to write it as h of t minus k, u of k. That's just by a change of variables. And now what do we know about this expression over here? We know that this expression over here, okay, is going to be equal to 1 for all values of k less than or equal to t, right? Because it comes from this expression over here. So for all k less than or equal to t, this is equal to 1. For all k greater than t, this expression is equal to 0. Okay? And so then this is equal to summation, go back to black, summation over k equals minus infinity to t now. It doesn't go beyond t. 1 times u of k. That's a discrete integration, summation, basically. It's a summation. Let me call it summation. So we are. That's a discrete summation, okay? So what we've seen now is that to add up a signal, to add up an input up to time t, we do this operation through a convolution operation. Okay? And that's a linear operation in the next few minutes. We're going to verify that that is the case. But this is how we do the summation. You sort of apply the formula directly in order to understand how to process an input to produce an output. Okay. Why is the convolution equation a linear equation, and why is it a time invariant equation? What do we mean by this? Okay, so in terms of linearity, what we're going to say is that, remember, I said the notation, we say y. We said y is equal to hu, meaning that h operates on u. So linearity for us means what? Linearity means if u is equal to u1 plus u2, or maybe a combination of that. Actually, let's do that. It's a little bit better. Let's say if u is equal to alpha 1 u1 plus alpha 2 u2, okay? Then we would like to say that the way this operator works, it works in a linear fashion. So the output is going to be alpha of hu1 plus alpha 2 of hu2. Okay, so is y equal to alpha 1 h acting on u1 plus alpha 2 h acting on u2? Is that the question? And the answer, of course, automatically is the case, because the way h operates on u is by multiplication and addition. And so that operation itself is a linear operation on u. So this is automatic. I don't even have to verify that for you. You can just write it down, right? And so this property actually is automatic. What about time invariance? And what do we mean by time invariance? And again, it's easy to verify these things, but what do we mean by them? So it says the following. It says that if I shift the input, does the output shift the same way? That is, this operation doesn't depend on where you start time. So how do we explain this? So let's say that, for example, my input, u, is shifted by an amount equal to capital T. So the input now is shifted by an amount equal to capital T. This is how I represent the shift. I subtract capital T from my index, little t. And so then, every value that was the value at 0 of this function, okay, it's the same as the value t of the original function u of t, shift by an amount t. Then the question is, what happens when H operates on U that is of T minus capital T? So in this new function U tilde, okay? So the rigorous way we do this is that to keep our notation right is to say this, let's say that this is a U tilde of time T. So a new signal that is equal to the original signal shifted by time capital T. So whereas the question is, what is H of U tilde? And we want to verify that, in fact, that's equal to Y tilde, where Y tilde itself is Y of T minus capital T. That is, if I shift the input by an amount T, then the same output that resulted from U is shifted by the same amount capital T. And again, that comes from the definition of the convolution operator, that it actually just multiplies and shifts and multiplies. So if the inputs get shifted, the output gets shifted. So again, I'll let you verify this, a very straightforward computation. But this property of time invariance is going to be crucial for us in looking at time series analysis, and in particular in trying to learn the underlying structure of a time series. A property that we look for is this time invariance, which means that somehow the underlying systems that we're learning are going to be linear time invariant systems. Well, at least for the first part of this particular course.